Determine the pH of a 0.2 molar acetic acid solution if the Ka of acetic acid is 1.8 times 10 to the negative 5. So this is a problem just like we've seen previously, in which there's just a weak acid present, and we want to find the pH. So solving this problem just as we've done previously, you can build a nice table, and you can plug in for the concentration of acetic acid beforehand and acetate beforehand. Changes in concentration, find the equilibrium amounts, and plug into the equilibrium expression, being able to cancel out negative x because there's a fairly insignificant reaction, and the value of x is going to be less than 5% of that initial 0.20 molar. So ultimately you get a pH of 2.72. But what if you edit this problem by adding that there's also 0.30 molar sodium acetate present? Now, sodium acetate dissolves in water 100% to give acetate and sodium. Sodium, of course, we know doesn't react with water. It has no effect. It's going to be just a spectator ion in all of our calculations, so we can ignore it from here. But acetate here, this is a common ion of acetic acid. It is the conjugate base of acetic acid. And being that it's a common ion, it's going to have large effects on the acidity of the acetic acid and of the pH of the solution. So, just like before, we can build a nice table and solve for the changes in the concentrations of all things. But there's a key difference here. And in the previous case, we saw that acetate had a solution molarity of 0 molar initially. But in this case, its molarity is 0.30. Now, having this significant concentration of our conjugate base of this common ion, this is going to greatly affect our calculations. You see, plugging into the equilibrium expression just as before, but this time having 0.30 plus x instead of just x, we are going to see that there's going to be much less significant of a reaction. You see, if you just have acetic acid present, then it might dissociate, and protons and acetate ions, they may not be very close to each other after dissociation, and therefore the reaction might go to significant completion. However, having a bunch of acetate already present allows for that acetate to combine with the proton and reform acetic acid to a much greater extent, so that the acetate, this common ion, actually prevents significant dissociation of your original acetic acid. We see that having a common ion present reduces the extent of reaction. And so we can consider that this positive x and this negative x are both going to be relatively insignificant for this weak acid and weak base solution. We can presume this if the concentrations of these weak acids and bases are greater than 0.10 molar, or 0.1 molar. That is, there's going to be a relatively small percent ionization. Although, if you had smaller than 0.1 molar, you might have a greater percent ionization, as we saw in our weak acids and pH video earlier. So, being able to cancel out this positive x and this negative x, then we get a much simpler problem in which we only have x here, and we're able to then solve for it and find that x is equal to 1.2 times 10 to the negative 5, that our pH is 4.92. Please note that in the original case, where we just had acetic acid, our pH was 2.72, a fairly acidic solution. But having this common ion present, our pH was 4.92, much closer to neutral. You see that the presence of a common ion greatly moderates the pH towards 7. Now, we could do calculations with these common ions in the future, but you'll actually save a lot of time by using the Henderson-Hasselbach equation, which I'll derive here. We see that Ka is equal to the concentration of protons times conjugate base over original acid. You can rearrange to find the concentration of protons from the Ka and the concentrations of our acid and our base. Now, it is only this simple It is only this case if we're able to get rid of those negative x's and positive x's, which we can only do if the reaction proceeds relatively insignificantly. Hence, this equation must follow some rules, some parameters, which I'll define in blue by Henderson-Hasselbach. But seeing this equation, we can further work it until we get pH is equal to pKa plus the log of the concentration of our conjugate base over our acid. We did this by taking the negative log of both sides of the equation. And pKa, that is the negative log of Ka, just as pH is the negative log of the concentration of H plus ions. So, taking this equation and seeing that A minus is a conjugate base and HA is an acid, we could more easily memorize it as the pH is equal to the pKa plus the log of the concentration of our conjugate base over our acid. pH is equal to pKa plus log of base over acid. This is the Henderson-Hasselbach equation, which we are going to use extremely frequently and is going to make our life so much easier. You see, the Henderson-Hasselbach equation uses the initial concentrations of our acids and bases, presuming that there are negligible reactions. What that means, though, is that if we're presuming these negligible reactions, this equation only works if we're dealing with weak acids and bases, as strong acids and bases have definitely significant reactions. They often will react 100%. And another thing then is that in order to have this negligible reaction, it can only occur if both the acid and the conjugate base are present initially. Okay, so only if the acid and our conjugate base are present initially. Otherwise, you cannot use this equation. Like we solved problems in our original acid and base chapter, you could not solve those problems using this equation because there were not common ions present. So let's resolve our common ion problem, but this time let's use the Henderson-Hasselbach equation. So we have the same initial concentrations of acetic acid and acetic acid and sodium acetate, and plug in then for the Henderson-Hasselbach, which is pH is equal to pKa plus the log of base over acid. pH then is equal to the negative log of Ka, because pKa is the negative log of Ka, and then add the log of the concentration of our acetate over our acetic acid. So then pH is equal to a negative log of 1.8 times 10 to the negative 5, that was our Ka, plus the log of our base, 0.30, sodium acetate, over our acid, 0.20 molar acetic acid. So we get pH is equal to 4.74 plus 0.176, or pH is 4.91. We see that Henderson-Hasselbach gave the same answer as when we solved using the ice table, except Henderson-Hasselbach is, oh, so much quicker. You'll love this equation. Please use it as frequently as you can if you're following the rules. You can only use it in certain cases. Thanks for watching, guys.